Hello everyone, hope you're doing well. We're almost done with building the parser, so just a few more keywords and we're actually finished with the hardest part of the self-hosted compiler, so more on that later this week. But just like when we built the Lexer, there have been some memory bugs that were hard to troubleshoot. And I've been able to fix them all, but I noticed a pattern. What I always need to do first is figuring out where things go wrong. And it was quite a boring process to do this by hand with printing values, then compiling and running, then printing other values, and continuing this loop until I found the issue. So for this video, I decided it's time for us to implement a keyword that will make our lives a lot more easier. And that's traceback. So I thought this keyword was interesting enough to make a video about. So yeah, let's do it. So you might know it from other languages, for example, Python. What if we create a function that raises a value arrow? Like this. And then maybe another function that calls that function. So if we call this second function, which calls this function which raises, we'll see a stack trace or a traceback. We know exactly which calls were made, and when you think about it, this list of function calls, it's actually a representation of the stack, because the stack contains different stack frames, and each stack frame corresponds with one call, one function call. For this reason, a traceback is sometimes called stack trace. So what do we want to do? We want to create this, but how do we do it? Let's say we have our stack here. Normally we push the arguments that are needed for a function call, and then when we actually call the function, the call will push the return value onto the stack. Then we push the old frame pointer, and then we execute the code within the function. And the frame pointer will point at this unit in the stack. Let's show it like we're having multiple function calls. So what we want to do, when the traceback keyword is executed, we want to go to the current frame and print the call that was made, information about the call. Then we want to go to the previous frame pointer and do the same. And repeat this until we're at the very first function call, which is the function call to main. So I think what we need to implement this and keep it simple is to add the information here. So when we call the function, we also push like a string, for example, in, I don't know, function foo online 1, 2, 3, something like this. So this is pushed onto the stack. And maybe a Boolean, which lets us know if it's the root function call. So maybe false here. And this would be true if it's the first function call. So something like this is what we want to build. Now, we don't have the luxury of the standard library. This traceback keyword is built into the programming language. So this means that something simple as printing values is done by crafting syscalls in assembly, probably. We could build the string inside the traceback, but for now I think it's okay to just build the string during compilation time and then simply push it the way I explained it here. Okay, so let's see what we want to do. So we want to push a string and a root call Boolean. When calling function. Okay. We want to change the offset to the arguments. because these are going to be offset by 2. What we want to do, we want to write a function to print stack trace. We'll do that in assembly. And then add a traceback keyword, which will be a jump to the stack trace program function. Let's call it function. So this is what we want to do. So pushing a string and root call boolean. That's quite easy. This is the Bootstrap compiler written in Python. So here in this call, we actually add the opcode for push string. This is where the string is built. So file name, the line, and the current function. And this is the boolean. I chose to make it true instead of false if you need to continue. This was easier for the assembly flow. So yeah, that's the first thing we needed to do. And we wanted to change the offset to the arguments. So for the argument, yeah, we have a get argument opcode. And this was on set to 1. So we added 2 more, so the offset is okay. So next up is actually writing the function to print the stack trace. To make things easier, I started out with creating a dot graph. All right, traceback. All right, so this is the graph, and it's quite simple. Okay, so we assume that a message string is pushed. The pointer to is pushed on the stack, so we pop it and save it in a register for later. Then we print the function call that's pushed together with the arguments. We print that, we check the main flag, the root function call flag. If it's false, so it's not the root, it's not the main function call, then we jump to the previous frame pointer, so the previous stack frame, and we repeat. And if it's the first call, then we print the error message that's saved in the register earlier. And then we end with exit code 1. So it's quite simple, but there's one thing. If we want to print the function call, if you check out the write syscall manual, what you'll see is it takes a file descriptor. Well, we know that, that's standard out, or standard error, actually. The buffer, well, we have that. That's pushed together with the arguments on the stack. But count, we have to actually calculate count. So that's the first thing you'll do in the function. And then you'll use the write syscall to print it to standard error. It turned out it's quite an extensive function. If you write it all out in assembly, I think I will rewrite it in terms of opcodes, in terms of the intermediate representation. So we don't have to rewrite it for different compiler backends, but I'll do that later. For now, it's in assembly. First thing we do is we pop the message pointer to register R8. Then we print the function call, and we start by counting. So the counter is RDX. RCX contains the current character. We'll put the current character in AL, and we'll test it. And if it's 0, then we'll jump out of the loop. Otherwise, we'll increase the counter and the character pointer, and we'll repeat. That's the loop that counts. And I made it so everything is in the right register for the syscall. So we only have to set RAX and RDI and then perform the syscall. So this prints the function call. Okay, then we'll check if the boolean that's pushed tells us it's either the main function call or not. If it is, then we'll jump to the end. And if it's not the main function call, then we'll move to the previous frame. So what we do is this is stack pointer, we'll move the frame pointer, current frame pointer into the stack pointer. Then we'll pop the old frame pointer to RBP. So after this, we have the old frame pointer in the correct register. And then we'll jump to the previous loop and print the next function call. But if it is the main function call, then we'll jump to this, so out of this bigger loop, and we'll print the error message, which was saved in R8. So we'll move it to RSI, and we'll actually do the same thing again. It's so we count how long the string is, and then we perform a write syscall. And when that's all done, we put 1 to RAX, and we jump to _end, which will exit with this exit code. So we exit with 1. And that will cover all of this flowchart. I think that's it. I've also added the traceback keyword. And like I said earlier, it's actually just a jump to the function in assembly we just created. So let's test it out. Let's see, foo.elo, and then let's say we have a foo function. Something went wrong. And traceback. And a bar function which calls foo, and the main function which calls bar. So let's see, the bootstrap compiler. Let's put it in test.asm and compile it. All right, that looks good. Something went wrong. And this is the stack trace. So if we look at foo, we'll see that this is the latest function call, which is on line 5 in bar. Yeah, that seems correct. And that originated from line 8 in main. Cool. With the file names and all. So yeah, that seems to work. Awesome. One other nice thing about this is that it's very easy to port because there are no new opcodes. It's just a jump, and we can just copy paste the assembly code we wrote. It's very easy to port, so I'm very happy with this new feature. Okay, yeah, like I said, I'm almost done with writing the full parser. I guess in a couple of days I can make a video about that, and maybe I'll even make the code generator, and we can try to have the self-hosted compiler ready this week. It might be quite optimistic, but I think it's something we could do. So yeah, thanks for watching. I hope you found it interesting, and hopefully I'll see you next time. All right, bye-bye.